Right now, as you hear these words, radioactive debris from a dead star is falling on you. Not metaphorically, not in some abstract theoretical sense. Actual atoms forged inside a star that exploded thousands of years before humans built their first city are raining down on this planet. And scientists just proved it. Here's the part that should keep you up tonight. We're not just passing through this debris, we're moving deeper into it. And there's one thing scientists found buried in Antarctic ice that tells them exactly how long this has been happening and what it means for what's ahead. In May 2026, a team led by nuclear astrophysicist Dominic Koll at the Helmholtz-Zentrum Dresden-Rossendorf in Germany published results that shook the astrophysics community. They'd done something no one had ever accomplished before. They turned 650 pounds of Antarctic ice into a flight recorder of Earth's journey through the galaxy. And the story that ice told was far stranger than anyone expected. But to understand what they found, you need to know what they were looking for. An isotope called iron-60. It's a radioactive form of iron, and here's what makes it so special. It cannot form on Earth. Not in volcanoes, not in labs, not anywhere on this planet. The only furnace hot enough to forge iron-60 is the core of a dying massive star. And the only event violent enough to scatter it across space is a supernova, a stellar explosion so powerful it briefly outshines an entire galaxy. Iron-60 has a half-life of 2.6 million years. That sounds like a long time, but on planetary timescales, it's practically nothing. Any iron-60 that existed when Earth formed 4.5 billion years ago decayed into nothing within the first 15 million years. Gone, completely. So if you find iron-60 on Earth today, it didn't come from here, it couldn't have, it arrived from somewhere else. Recently by cosmic standards, and the only way it gets here is if Earth physically flies through a region of space where a star once died. That's exactly what Koll's team went hunting for. They transported 295 kilograms of ice, that's nearly 650 pounds, from the Alfred Wegener Institute in Bremerhaven to Dresden. This wasn't ordinary ice. It came from the European Project for Ice Coring in Antarctica, known as EPICA. These cores contain layers of compressed snow dating back 80,000 years. Each layer is a frozen snapshot of whatever was floating in Earth's atmosphere at that time: volcanic ash, pollen, cosmic dust. After months of melting, filtering, and chemically separating the contents, those 650 pounds of ancient ice produced just a few hundred milligrams of dust, a tiny pile you could fit on your fingertip, and inside that pile, they found it. Iron-60, atoms born inside a star that no longer exists. But the real discovery wasn't just finding it, it was the pattern. The team compared iron-60 levels across 4 different time windows, from 80,000 years ago, all the way to modern Antarctic snow collected in previous studies. And what they saw was unmistakable. The older ice, the stuff from 40,000 to 80,000 years ago, contained significantly less iron-60 than the newer samples. The signal was getting stronger over time. Let that sink in. Earth isn't leaving this debris field behind. We're flying deeper into it. Our solar system is currently moving through something called the Local Interstellar Cloud. Think of it as a vast, invisible fog drifting between the stars. It's a region of slightly higher density gas, plasma, and dust that stretches across several light years. Scientists have known about it for decades, but they've never been able to study its internal structure directly. Telescopes can see the cloud's edges, but from inside, you can't see the walls of the room you're standing in. That's where the Antarctic ice comes in. Because here's the part nobody talks about. This ice isn't just a climate record, it's a galactic navigation log. Every layer records how much cosmic material was falling on Earth at that point in time. More iron-60 in a layer means we were passing through a denser part of the cloud. Less iron-60 means a thinner region. The ice cores essentially created a map of the cloud's internal structure, drawn not by a telescope, but by Earth's own journey through it. And that map tells a story. The solar system entered the Local Interstellar Cloud somewhere between 40,000 and perhaps 124,000 years ago. At first, we were in a relatively sparse region. The iron-60 drizzle was light, but as the millennia passed, we drifted into thicker territory. The drizzle became heavier, and right now, today, we're in one of the densest sections we've encountered. Now, before you start building a bunker, the iron-60 falling on Earth is extraordinarily faint. We're talking about individual atoms scattered across tons of ice. It poses zero biological risk. You breathe in more dangerous stuff walking past a diesel truck, but the implications of this discovery are enormous. Remember that question about what's ahead? Scientists now know the cloud surrounding our solar system was directly shaped by a supernova. Not a theoretical supernova, a real one. The Iron 60 is the chemical fingerprint, the smoking gun. Somewhere in our galactic neighborhood, a massive star died violently, and the cloud we're flying through right now is its corpse. The scattered remains of a star that once burned brighter than 100 million suns. And our neighborhood has seen a lot of death. The Local Interstellar Cloud is just one of roughly 15 similar cloudlets drifting through a much larger structure called the local bubble. This bubble is a void in space, hundreds of light years across, carved out by a chain of supernova explosions in the Scorpius-Centaurus stellar association starting about 10 to 15 million years ago. Multiple stars detonated one after another, and their combined shockwaves hollowed out a cavity in the galaxy. We live inside that cavity, swimming through the debris those explosions left behind. The team's findings ruled out the only competing explanation. Some scientists had argued the Iron 60 might be the fading echo of much older supernovae that happened millions of years ago, a signal slowly dying down over geological time. If that were true, the Iron 60 levels would decrease smoothly and gradually. Instead, the data shows sharp variations over just tens of thousands of years. The signal jumps and dips. That's not a fading echo. That's the texture of a cloud we're actively passing through. Think about what this means for you. Every breath you take contains molecules that were recycled from ancient stars. That's not new. Carl Sagan told us that decades ago. But this is different. This is not about atoms from billions of years ago that became part of Earth's original recipe. This is about fresh deliveries, material arriving right now, today, this week. Cosmic ash from a dead star, drifting through our atmosphere, settling on Antarctic snow, landing on rooftops, dissolving into oceans. You can't see it, you can't feel it, but it's there. And the amount reaching Earth is increasing. And here's the question that keeps the researchers up at night. We know that in the distant past, Earth passed through much denser supernova debris. Those events left massive Iron 60 signatures in deep-sea sediments on the Pacific floor, dating back 2 to 3 million years, and again around 6 to 7 million years ago. Those encounters were far more intense than what we're experiencing now. And some scientists have begun asking whether those heavier bombardments left marks not just in the rock, but in the history of life itself. Changes in cosmic ray flux, shifts in cloud formation, alterations in the radiation environment that every living thing on this planet depends on. We don't know the answers yet, but for the first time, we have a tool to look. Antarctic ice has become a telescope pointed not at the sky, but at the path beneath our feet, a record of where we've been, written in atoms that had to travel across the galaxy to reach us. Koll's team is already planning their next move. They want to analyze even older ice from periods before the solar system entered the local interstellar cloud. If they can find the transition point, the moment we cross the boundary from open space into this supernova remnant, they'll know exactly when our journey through the debris began. The Beyond Epica project is drilling for the oldest ice on Earth, reaching back over 1 million years. That ice might contain the answer. And there's one more thing worth considering. Scientists estimate the solar system will exit the local interstellar cloud within a few thousand years. We'll leave this supernova debris behind and enter whatever lies on the other side. A different cloud, open space, maybe something we haven't even imagined. Nobody knows what the interstellar environment on the far side looks like because we've never been there. Not in recorded human history, not in the entire existence of our species. We've always thought of Earth as sitting still while the universe moves around us, but we're not still. We never were. We're flying 20 kilometers every second, 72,000 kilometers every hour, through the graveyard of a dead star. And the proof was waiting for us, frozen in ice at the bottom of the world for 80,000 years. Scientists just had to melt it to hear what it had to say. What would you want to know about the next cloud we're heading into? And does it worry you that no one's looked yet? Tell me in the comments.